In this part of 7.2, our objective is to find the volume of solids with known cross-sections. This is different from what we did in earlier of 7.2 because these are not going to be solids of revolution like the other ones. However, the important thing to remember is that no matter what kind of solid it is, the volume remains to be the integral of the area of a slice or the area of a cross-section, but it's always volume is the integral of the area of a cross-section. And that's what it shows in these integrals here, is that if we have a cross-section or a slice, as I'm calling it, perpendicular to the x-axis, so cross-sections, when they are perpendicular to the x-axis, it is a volume is an integral of the area with respect to x, functions of the area with respect to x, versus when the cross-sections are cut perpendicular to the y-axis, it's going to be the integral of the area of a slice, but the area is functions with respect to y. Let's take a look at what it looks like when we explore these solids. So the first one is finding the volume of the solid whose base is enclosed by this equation. What's this an equation of? Well, you have to know that's an equation for a circle. What about the circle? Its center is at 0, 0. Nothing subtracted from x, nothing subtracted from y, and the square root of 1 is 1. The radius is the square root of this number, which is 1. So we are plotting our center and going out from the center 1 unit in each direction. Now, again, to maximize our space, I am using 4 blocks to represent 1 unit. So once I've graphed those 4 points, I can get a decent idea of what the circle looks like. So please keep in mind, this is the base of our solid. The base is enclosed by that circle. I like to shade lightly the base of the solid. Now just lightly, because I don't want to not be able to draw on it and not be able to see what I've drawn on it. The cross sections now, the cross sections of my solid will be taken perpendicular to the base, Well, they didn't specify perpendicular to the x-axis or y-axis. Why not? Well, because it's a circle, it's symmetrical. So let's take it whichever way we want to. In fact, let's choose perpendicular to the x-axis just to keep things a little bit simpler, more straightforward this time around. So since we have a choice, we will go perpendicular to the x-axis. Now, I don't like to slice right down the middle because sometimes that can give us a false impression. So I'm going to show one of the slices off to the side like this. So this is a bird's eye view of one of the slices in that circular base. These cross sections now are equilateral triangles. So imagine being able to build a triangle that's coming out of the screen at you three-dimensionally. Can you imagine that? It's quite difficult. So let's try this. Here is a circular base like we graphed to begin with. If I slice perpendicular to the x-axis, this is our bird's eye view. This is what we see, those slices. Now, if I drop the y-axis flat, you can start to get an idea that this is going to be the flat surface on which I'm going to build the cross sections. Now remember, our problem said the cross sections are equilateral triangles. Let's see a few of those slices. Well, there they are. So imagine it's kind of like taking a cake pan and putting the cake slices in there, and this or bread slices, maybe, some sort of slices. In this example, our slices are equilateral triangles. Well, we have an infinite amount of them, and they're going to fill up that entire base. So one of them swept across the circular base. Notice how it's changing in size depending on where it's located. Let's go ahead and create that entire solid by sweeping those triangles through and letting them fill up that space. So here's our three-dimensional solid that you're going to have to imagine. I'm going to show the entire solid and perhaps those 4 cross sections again. So you get an idea of, we have the circular base and the 4 cross sections in that base. let's go back to the problem that we're trying to draw. So you're trying to imagine that triangle coming out, but it's not going to the right, so I don't like to draw it going to the right. It's coming out at you. So here's what I like to do. I've drawn the region. I draw the cross section, the bird's eye view, and then I draw the entire cross section, the frontal view. So imagine I've sliced this from a bird's eye view, and then I've peeled out the slice, and here's what the slice looks like. An equilateral triangle. Remember what equilateral means. All three sides are congruent. Now, remember our goal is to find the volume of this solid. And remember that volume is the integral of the area of a slice. Well, what's the area of this triangle? Area is always, for a triangle, 1/2 base times height. How long is this base? Well, where did it come from? The base, this right here, this length of the side of the triangle, comes from this circle where it went from here down to here. That, in fact, is the length of that base. Let's call it B here, for the base that we're plugging in there. How about the height of it? Well, let's stick with one thing at a time right now, because remember, when we slice perpendicular to the x-axis, that means that our volume is going to be with functions in terms of x. So when we go to our volume equation, we know will be in terms of x. So how do I write my base, b, in terms of x? Well, b starts up here, b ends down here. So the length will be measured from top to bottom. So we will measure it top minus bottom. Well, if it's on top, that's half of the circle, and if it's with respect to x, I have to take my equation of the circle and solve in terms of x. So y squared equals, subtract x squared, 1 minus x squared, then take the square root, plus or minus the square root of 1 minus x squared, where the top half is the positive square root of 1 minus x squared. The bottom half is the negative square root of 1 minus x squared. So top minus bottom becomes square root of 1 minus x squared minus negative square root of 1 minus x squared, or 2 square roots of 1 minus x squared for short. So that's how we can represent B, the base. But again, what about the h? Well, let's take a look about the h. I'm going to draw the height of the triangle in, perpendicular to the base. I'm going to label that h. What are some other things I know about an equilateral triangle? Well, all the angles are congruent, therefore they're all 60 degrees. Therefore, when I draw this height, that becomes 30 degrees. Well, in a 30, 60, 90 triangle, the sides are related in this way. Well, actually, let's start with this. The height that's drawn to the base is cutting the base in half, so that's base divided by 2. And just to be clear, I'm going to make that actually look a little bit more like an H right there. Very good. The height in this picture is the long leg of the 30, 60, 90 triangle. Therefore, the height, that leg, is the short leg times the square root of 3. If you're not sure, you can always use the Pythagorean theorem, where we know the hypotenuse is also b, because this side was b, and you can use c squared equals a squared plus the other guy squared, right? Now, we know that the h is actually over here, b over 2 times square root of 3. So really, our area formula can be written as 1/2 b times b for b squared times square root of 3 over 2, or better yet, square root of 3 over 4 times b squared. Yeah, there's some work to do to remember your geometry. Let's go ahead and plug our b into there, so square root of 3 over 4 times 2 root 1 minus x squared, base got squared. Once I have my area, it's quite simple. I plug it into my volume. Integral of square root of 3 over 4 times 2 square root 1 minus x squared squared. Say dx. You can simplify this if you want to, and then because we're with x's, we have to figure out where does our region start? -1. Where does our region end? +1. So -1 to 1. Feel free to simplify it before you integrate. It could make it easier. Isn't that cool?